we shall continue our lecture with our triple essay. So, we start the point where we have left in our previous class. So, this is the expressions that this is actually the observation we was discussing. So, you can see that, so there is a part here and this is the uncompensated one and this is due to the compensation. Ultimately, the power handling capability of the transmission line increases the value of the VQ. And what is the beauty of it? Even you can transmit power at 0 delta. So, this is a enhanced power handling capability in percentage is huge when delta is very low. So, it is a very suitable kind of compensation when delta is very low. So, this series capacitor increases the transmitted power by a fixed percentage with the fundamental with the transmitted power of the uncompensated line and delta. Moreover, the SSC can increase the fixed fraction of the maximum power. So, you can see that when it can increase transmitted by the uncompensated line and this is actually independent of the delta. So, for this reason this is the K where it is an uncompensated line where K equal to 1 by 5 is a ratio of V by VQ and this is 1/3. You can see that even at 1/3 voltage at 90 degree power handling capability increases to 50%. So, this is the delta versus power and power graph. You can see that you can make the power negative also. So, this is the VQ equal to 0 uncompensated line and you can make VQ negative and thus you can bring power in reverse direction and similarly you can increase the power to 1.5 per unit at 0.7 VQ. The normalized power PQ versus angle delta plots the parametric function for VQ for different values of the VQ, it is 1 by root 2 0.707, 3.53 minus 3.53 and minus 1 by root 2 or 0.707 and this is a different value for the K. So, what is the principle of operation of the SSC? The SSC can decrease, this is one of the best features of it, as well as increase the power flow in same degree by simply reversing the polarity of the injecting AC voltage. So, it can inject plus VQ or it can inject minus VQ. If plus VQ increases the voltage capability, you can reduce the capability of the line by injecting minus VQ. The reversed or 180 degree phase shifted voltage adds directly to the reactive voltage drop of the line as if reactive line impedance is increased. So, power transmitting capability will decrease. If this reverse polarity injected voltage is made larger than the voltage impressed across the uncompensated line by sending end and the receiving end voltage, that means if VQ is actually more than Vs minus Vr, then power will reverse with the line current will also reverse and I equal to VQ minus mod Vs minus Vr by x. So, current will flow into the negative direction. So, that is also possible. Please see the compensation. So, let us try to understand this graph. This is actually without compensation where voltage and current are assumed to be in a phase. Now, you will have a positive compensation and thus current increases. And what happens thereafter? You will have compensation for the negative power flow. So it will become 180-degree phase shift. So this is voltage and this is current. So current is flowing in a negative direction. What happened to the P and Q? Here actually the Q was this, here P was this and Q was this. So here you have increased the P. So power handling capability of the line has increased. Now here it will come down, and this is the reactive power. Reactive power initially will be low, thereafter it will increase as increase little bit, thereafter it will be actually in a positive in nature, because here PQ is positive. And this is the injected phase A. Initially you were not injecting almost any current. Now you are adding some amount of voltage in quadrature. So they are out of phase by 90 degree, and see that here also the same thing will happen, but they will be in outer phase by minus 90 degree. And this is the curve for injected Q. Initially it is almost 0, thereafter there will be a little bit of small q, and this will be actually little bit of more q, that will add up this q. So this is the principle of operation of SSC. SSC connected with the AC system for no compensation VQ for the time, say let us say 0 to T1, and purely reactive compensations for positive power flow PQ equal to Ix minus Vs minus IR, and this is for T2, and purely reactive compensation for negative power flow where VQ equal to Ix minus mod Vs minus IR, it is for the time T2 to T3. This is the principle of operation of VCSC. So what we can conclude from this discussion? Apart from the bidirectional compensation capability, the basic operation characteristics of SSC also have some additional advantages. SSC should not be tuned to any finite line inductance to have a classical series resonance at a fundamental frequency. So never resonance will occur and high current will flow. This is one of the disadvantage of this power system. SSC injecting compensating voltage is said to keep the control, and it is independent of the network impedance changes. So the control range of the SSC. So ultimately what we can see that, so you can make VQ minus and plus, so it can go either direction, but current has to be here unidirectional. So this will operate in first and the fourth quadrant of the IV characteristics. So SSC can provide the capacitor and the inductive compensating voltage independent of the line current up to its specific current rating as chosen by the device rating. So thus in voltage compensation mode, the SSC can maintain the rated capacitor or rated inductive compensation voltage in the face of changing the line current, and theoretically the total compensating current ranges from 0 to IQ max. So it can compensate this voltage VL to VQ to any level of current, and this is restricted by this current limit is restricted by the device rating. And Corresponding to the, now let us come to the loss aspect of it. Corresponding to the loss, as percentage of the capacitive or the inductive rating of SSC versus characteristics. This is the characteristics of the SSC and this is the loss characteristics. Of course, loss highly depend on current. Since you have employed the switches, so it is linear with the current. So, wear rating of the SSC is simply the product of the maximum line current at which the compensation is still desired and the maximum series compensating voltage, that is the wear rating, that is I max into V max. So, this is the this rating and we require to find this rating and this will be I max into V max is a constant. So, thus it gives you almost a rectangular hyperbola. So, ultimately we require to operate this VQ below the VQ max. The control range and the wear rating switches of the SSC. The impedance compensation mode, the SSC established to maintain the maximum rated capacitive or compensating reactance at any line current up to its rated voltage, up to the rated maximum voltage. Thus, what happened? The corresponding loss versus line current characteristics is shown here. For this reason, this is the IQ max and ultimately this is I and this is the loss and this is the current rating of the devices. And thus what happened, that is actually will change accordingly. So, we have to keep this below the IQ max, otherwise the maximum voltage or current limit may cause. For variable impedance type compensator, I max may be separately defined by the rated maximum steady state line current. The basic wear rating of the major power component of the SSC, these are mainly nowadays IGBTs or sometimes GTOs, must be rated for this currents. For this GTO is chosen and for the relevant maximum voltage. So, let us take some practical application of the SSC. In some practical application, only capacitive series line compensation is required. So, inductive is not generally required and black flow of power is not also required. This is just to show, we have shown that curve to show that it has got that capability. Yes, it can do that. In these cases, as well as in those which already use or plan to use the series capacitor as part of the overall series compensation scheme, will be followed in this case. So, SSC may be combined a cost effective a fixed capacitor, that mean SSC will have a rating of 0.5 pu and the rating is combined with the fixed capacitor of 0.5 pu. So, total compensation will be 0.5 pu and this one is gives you the 0.5 pu and other this SSC will give you the 0.5 pu, because most of the cases we require to compensate, we require to have only series compensation for the capacitive kind of thing. So, we can put this kind of thing, so it can go positive and negative and thus add up and this will go, this can make it 0 by actually injecting minus VQ. So, this is the way we can operate and thus what happen, we can reduce the rating of the switches that use for the SSC. So, this is called definitely, as we have seen, that hybrid TCR or hybrid STATCOM. So, it is actually the hybrid SSC. So, this is the VL and this is VL max and this is a VQ max IC. Ultimately, a constant amount is been added by Vc, so thus it is shifting like this, and otherwise if it is VL, net lying becomes 0, and when both the constant Vc and this it changes, so this gives you this much of Vc. Similarly, Vq equal to IL max and effective equivalence impedance becomes Vc plus Vq, and in this case it becomes Vc minus Vq. So, this is a impedance compensation mode in case of the hybrid SSC. Now, voltage compensation mode similarly, and what about to the losses? Since loss also will be reduced because this rating is 0.5, not 100%, and this is the new VQ max rating, and it will, and this is the VQ 0 rating, and it has to be operate within this. Similarly, this is for the impedance compensation mode, and this is actually VQ max, the upper trajectory, and lower trajectory VQ equal to 0, where it is not injecting any current, it is a capacitive kind of thing, and losses is due to the flow of current. So this will be the lower one, and this band essentially is for switching. Losses versus line current characteristics of SSC and fixed capacitor arrangement. Now, real power compensation with SSC. So, it can compensate for the real power. So, this is the one of the basic features of the SSC or any series compensation. In contrast to the series capacitor, SSC can negotiate both. We have assumed that actually VQ is perpendicular to the I, that is the current. For this reason it is only compensating the reactive power, but we can have a real power compensation. SSC can negotiate both reactive and the active power with the AC system, simply by controlling the angular position of the injected voltage with respect to the line current. So, thus the voltage source converter play an important role to generate a voltage that required to be injected in such a way that it can also inject the real power. As explained previously, the exchange of the reactive power requires that a DC terminal of the SSC converter, or we require a storage element, and to be coupled with the storage element or the storage source. So, it can be battery or solar panel or any kind of thing. The capability of the SSC to exchange simultaneous compensation of both reactive and the resistive component of the series line impedance in order to keep the X by ratio high. So, this is the one of the desired features of the SSC. Generally X by ratio is taken to be 10 or something like that. But series capacitor compensation would further reduce the effective resistive to the resistive line impedance of ratio. That is one of the problem of it, because when you are basically it became XL minus XC. So, this ratio by R get decreased, but we cannot, but in this case it is possible to maintain the X by R ratio. So, then what happened? The line impedance ratio progressively increasing the reactive power demand of the line and the associated line losses and the possible voltage depression would start to limit the transmittable reactive power. So, voltage sag and other. For normal range of control, the line whose uncompensated X by ratio is chosen to be 7.4. That is what I was saying, that in previous slide this ratio is around 7. And now let us understand this, actually the phasor as well as the circuit. By applying or increasing the series capacitive impedance, let us say 50% or 75%, the effective X by R ratio get decreased to this percentage as well as this percentage. Then what will happen then? So, see that this is actually the phi equal to 0, this is the compensation, and this is a 75%, this is 50%, and thus what happened, you can see that this is R equal to 0 and this ratio is actually 7.4, and this is X by X ratio is 3.7, this is 1.5, and thus in this way changes. Then what happened? This poses the line resistance power transmitted increased by the series capacitor compensation, and our assumption no longer hold good that actually line is predominantly resistive, predominantly inductive. Now, the result of this reactive compensation of the line current sin I sin delta by 2 plus phi supplied by the receiving end system progressively increases. That is the one of the disadvantage. So, the real component, that is I cos delta by 2 plus phi transmitted to the receiving end progressively decreases with respect to those would have been obtained in the ideal reactance slide when R equal to 0. So, this is the disadvantage, the reactive power handling capability decreases if the X by R ratio decreases. That is what will happen. So, you have to change this value. The transmittable reactive power P and the reactive power Q supplied by the receiving end bus can be expressed for the simple two machine system as a function of the reactive line impedance effective. So, we have to incorporate now the value of R in the line resistance R and the transmission line angle delta as follows. So, it will be V square by S square plus R square into X sin delta minus R 1 minus cos delta. Effectively, you can couple it. So, this will be the new equation for transmitting power with reactive power compensation, and thus what happens? You can see that line changes. So, this is the uncompensated line where actually X by L ratio, XL by R ratio is around 7.4. But when this ratio changes in a compensated line, then what? Then this is the case for uncompensated line having X by L ratio equal to 3 by 7. Similarly, this is the ratio of uncompensated line for X by L ratio equal to 1.85. So, you can see that drastically power changes, and thus if you can make this thing to the work properly with compensation, it will go to this point having X by L ratio 7.4, and it will be actually here, it will be shifting this direction, and similarly it will be shifting further here. So, what happened? So, real power compensation capability will drastically decreases, and this is the case where X by L ratio is very high. So, this will be the actually the ideal case where two machine theory will hold good. Now, with this observation, what we can conclude? The real power compensation capability could also be used effectively in minimizing the loop power flow by balancing both the real and the reactive power flow in the parallel lines. Simulation of the two machine system compensated by SSC with a DC power source or the storage element illustrate the combined compensation of the line reactance and as well as the resistances. The plot shows in the previous curve that the line current I and the phase A together with the uncompensated together with the corresponding receiving end voltage were VR equal to V 2. It shows transmitted power P together with the reactive power Q supplied by the receiving end. Moreover, it also shows the line current I again in phase A together with the voltage VQ injected by VSC. The active and the reactive power in the SSC exchange with the AC system via series voltage injection for no compensation when VQ is 0. Purely reactive compensation and reactive plus resistive compensation can be also done here. It can be observed in the previous curve that the additional resistive compensation increases with the transmitted power significantly. It also decreases with reactive power demand at the receiving end. So, this is the few characteristics of real power flow through the SSC. So, let us see that. Same thing, this is with no compensation. So, there is a little bit, this is a line voltage, and what happened then? SSC provide both reactive and the resistive power line compensation, and ultimately it is providing the P, this is actually P now, and this is the Q. Thereafter capacitive compensation comes, and so this is then actually the power rating increases. Then capacitive as well as reactive compensation comes, that is through the actual injection from the DC source or the storage element. Thus actually power handling capability of this SSC has increased, and this is the phase line, and initially current was small injected current, thereafter it is increasing and similarly it will continue. This corresponds to VQ, the voltage injected, and this corresponds to the line current I. And this is the injected real power and the imaginary power. Initially there is no compensation, so it is not injecting any PQ, and this is a capacitic compensation. So, there will be a Q, there is no P, and here both P and Q is present since it is inserting both. Thank you for your attention. We shall continue with our next discussions, a few slides, few discussion left also with our SSC, and thereafter we shall go to the next called actually PR, power angle regulator.